Alright, so what I have up here is I have the graphical representation of both my velocity and my position. My positional values up top, you can see it says x max sine omega t. My velocity values are on the bottom. I have x max times omega times cosine omega t. Now remember that x max times omega is nothing more than maximum velocity. I mean, it's all it is. It represents maximum velocity. Now, take a second or two to take a quick look at this graph and see if there's any major differences between the two of them. Okay? Now, hopefully you saw that the frequency remains the same. The angular frequency remains the same. If I were to go boom, 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 making a sound every time I hit the origin or hit the equilibrium point here, I would get the same frequency. It's going to be a little shifted. Boom, boom, boom. Same beat. So I'm going at the same angular frequency. That doesn't change between position and velocity. That's still the same thing. It's still the rate in which things are happening. Okay? Cool? Now the other thing that hopefully that you noticed is that the top of this peak and the top of this peak are not of the same elevation. The only way that would be true is if they were the same elevation, is if your angular frequency was 1 radian per second. That's the only way that those things are going to be the same. Now, normally what you end up having is that your velocity values tend to be smaller than your positional values. Normally. That doesn't always happen that way. There are some cases where your velocities can have a much higher value than your positional values, but for typical cases, the amplitude here is going to be greater than here, or less. Amplitude here is typically going to be less than the amplitude here. Now, you should be also careful to realize that this is nothing more than position, which we represent by meters. Why this over here is meters per second. So they're not exactly the same graph. They're different graphs. They're representing meters, positional values. This one's representing velocity values. Now this, the axes here, my y-axis or my x-axis is time. That remains the same. Every step, as you can probably, if you look really closely, there's marks here. Every single one of these marks is representing a step in time, and it's the exact same step, whether it's the positional value or the velocity value. Okay? Now, another thing that hopefully you notice is that there is something strange going on here. When the position of the object is at the equilibrium point, at the center, like I said, once again, if you want to consider that the origin, that's fine. At the equilibrium, that the velocity values have reached a maximum. They're the maximum possible velocity that that object's going to have. So that means as an object is oscillating up and down, up and down, up and down, the fastest that object is going is at the center. Okay? That's the fastest the object is traveling as it's going through that center point. Okay? Right there at the center, the velocity is equal to a maximum. Now, where is the velocity equal to 0? If I go ahead and I trace it out here, here's my next one. Boom. My velocity is equal to 0 here when my position is at its maximum. And that sort of should make sense. Now, velocity is change in position over time. Okay? So when the velocity is equal to 0, it reaches the top of its motion, and for a brief second, nano, pico, whatever you want to say, at that point, the velocity is equal to 0. It has to be. The velocity is not equal to 0, the object will continue to travel up off the screen. The velocity will continue, or the object will continue to travel up until it reaches 0. Okay? So it reaches its maximum position in the x direction and then heads back down. Okay? So right at the very top, the velocity is equal to 0. See, maximum, if I take that point down, my velocity is equal to 0. So at the very top, my velocity is equal to 0. It has to be. If it's not, that object continues to keep going up. At that point of 0, it's like, stop, going in the opposite direction. Okay? Cool? So, basically the same kind of geometry, or the same kind of shapes going on here. We've got a little bit of a shift here. If we were to talk about phase shifts, it looks like this is off by about 90 degrees, or half a pi. Okay? But that's what's going on here. They're basically the same. They basically have the same shape. The velocity shifted over a little bit so that when the object is at the middle, the velocity reaches a maximum. Now, I want to also talk about this point right here, the next point in this series. Once again, my position is equal to 0. So you want to think of the velocity being at a maximum at that point. The truth of the matter is that its smallest value, it's a negative value. It has the same magnitude as this velocity max. It's just going in the opposite direction. Positive velocity as the object is moving upwards. So as it's traveling through the origin, you know at this point that the object is traveling through the origin going up, where at this point it's traveling through that origin, that equilibrium, heading down. But they're both traveling at about the same speed at that point. Okay? So that's a comparison of the position graph versus the velocity graph for simple harmonic motion.